Ready. Let's get rolling here. Got a lot to get through. If you have any questions, please jump in. However, you can type them into the chat if you want. Tanya is going to be kind enough to try to monitor those, because when I get into this, I can kind of, lose the rest of the world. So this one, and just a little bit about myself. I'm the head coach of Team 3023 Stark Industries. My first year of coaching was 2010 Breakaway. Great season. I loved it. I didn't actually choose our team name Stark Industries, but we have gone full tilt into that, and I love it. Iron Man's only superpower is that he knows robotics, and that is just amazing. Something to think about this year. This is a joke I've been saying a lot with people, is just that 2020 is a dumpster fire. And this year is going to be very different for us. And so I've tried to change my presentation a little bit to monitor or to modify to that end. But something I've been joking with my team and my kids, 2020 is a dumpster fire, but robotics, our team motto, our official team motto is make it work, because that's what I say to the kids all the time. And so how do you make the best of this situation? And the answer is we're going to try to make s'mores. So that's the joke. We're making s'mores over a dumpster fire. That's how we say that we're trying to make the best of this situation. And as we go through this presentation, as we try to think about how this year is going to be very different, I want you to think about, there's two main aspects, game design and then the at-home challenges that people are participating in. But depending upon how much access you have to your robot, because your school's closed down, you may not even be able to do the at-home challenges. So you're going to be focusing mostly on game design. And that's what I'd like you to contemplate. And kind of that's what I've been thinking about as I was creating this PowerPoint presentation. There's a really fascinating discussion on Blue Alliance. And they have this, like, what makes a game good? And they have this ranking system. I don't know if I necessarily agree with their weighting of everything, but these are some of the things my team has been thinking about as we try to do a game design. And so we're going to go through a lot of past, my other two presentations focused on game pieces. And there's this big, long, like several slides that all focus on just game pieces. And this one, the PowerPoint, this aspect is more about field elements. We're going to be, I'll show you all the field elements that have happened throughout the history of FIRST. But I'd like to point out, this is an amazing year to prototype and do some of those things you've always said, well, we've never built a winch or a shooter or a climber or anything like that. Well, this is the perfect year to put in some time prototyping. So part one and two were on intakes. You can go back those slides. This recording is all posted on the Jumpstart website, and this one's going to be about kickers and catapults. Honestly, the kickers and catapults should have been with the game pieces, but I just couldn't fit them all in. So first question, what's a manipulator? And the official definition is any mechanism on the robot that is used to manipulate or interact with either a game piece or a field element. But if you've been to one of my presentations before, you know the joke on this one. What is it that most robotics kids say when you ask them, what is the manipulator? Type your answer into the chat if you want to play along. But I think we all know that most students don't rattle off the definition that's up on the screen. The other things that we're going to do today, there's going to be more like annotation and put stamps on the screen because it's hard with the chat. But this one, most kids they're like, it's the thing that's not the drivetrain. There's drivetrain and then everything else. And this one is going to be about, this session, we're talking about game field. And the first question you have to ask yourself is, what are you manipulating? And in this one, we're talking more about field elements. And so most of the games in the history of FIRST were game piece only. This is the first year, 92. Maze craze, they had to drive through corn. That was crazy. The rug rage, this was weird. And like in these competitions, you were on your own. It was one bot. Like this one was 4 bots. Each bot was on their own. Same thing with the corn situation. This one was interesting. It's like a giant circle. But again, game pieces only. There was no real manipulation of the field. 95 was game piece only, same for 96 and 97. But you'll see, and if you've been to my other presentations or gone through those slideshows, you'll see that there's a lot of situations where you have these giant exercise balls, and those come up a lot. Ladder Logic, 1998, that was game pieces only. Double Trouble, same thing here. And now 99, that was a weird year with the floppies. But finally, now here, 2001 was the first year that we had a field elements to manipulate, which was a balance bridge. And for those of you who this looks familiar, this is the exact bridge that was used in 2012 Rebound Rumble, which you'll see in a little bit. First time we did a bar hang was 2000, and that one you're going to be watching for. Zone Zeal, this is the one that people talk about as the famous chokehold maneuver, where a team grabbed all three of the scoring containers and yanked them over to their own side, but it was a game piece only game. Same thing with Stack Attack. There were totes, and you could just drive up full on and just bash into them, which would have been really fun. All right, this one, 2004 bar hang. Now, I've got to show you the most insane recovery. Now, this is from 2004. We had digital cameras, but digital like video was not as common. They do a replay in a moment here. All right, now, sorry, the audio is still going here. I can't imagine what it would have been like to be that driver for that robot, or for the team or the coach when that robot looked like it was about to tip over, but somehow managed. That was one of the first bar hangs that you see where it was crazy high up. The other ones were pretty low down. 2005 game pieces only. Same. This one, 2007, for those of you who built ramps, which is now in my team, we had ramps and they were disastrous for us, but Power Up was not the first year that teams were encouraged to have robots drive up on top of other robots. It happened in Rack and Roll in 2007. And the main reason I go through all of these things is because there's nothing new under the sun. And when you see a challenge, like in 2012, when we saw the balance bridge, and I'll get to that in a sec here. But if you didn't go back and look at how teams address that the first time it happened, then there's a lot of knowledge that's built up there. Same thing here. My team, if you don't look back at what teams did in 2007 for getting a robot up off the ground, then you're at a disadvantage. 2008 and 9 were game piece only. 2010, this was my first year as coach. And I just thought, like in this year, there was an end game and the robot had to climb / hang from this bar, and you'll see a beautiful example of a robot that does that. But see, here's the thing. I thought end games were just like always the thing, because this was my first year coaching and there was an end game. 2011, you had to manipulate. There was a post, you had to send a mini bot flying up that. 2012, there was a balance bridge. And right here, if you didn't watch, there were every year after the game animations release, there's Field Element videos that first puts out. And if you did not look at those Field Element videos, you wouldn't have known that you had to be able to, if you're building one of these at home, it was a 4x8 sheet of plywood. And if you did not balance it properly and support it, it had to be strong enough to support 2 batteries 28 inches away from the center. And so a lot of teams built manipulators that couldn't push with enough force. The other thing that you may not notice in this game, there was a 4-inch barrier, which is identical to the barrier that we had to cross in 2016 during Stronghold. That was one of the defenses. 2013 pyramids. Now this is why I was shocked when in 2014 there was no endgame. Also, there was this giant bar. 2014 aerial assist, we had to throw the giant things over. There was this giant bar. I thought surely we had to hang from that sucker, and I was convinced the entire season that they were going to come out with an update that was like, oh yeah, there's an end game, but alas, never. 2015, no end game, no hanging, no field element mechanism. 2016, they made up for everything. There were barriers and also a hang on top of that. 17, rope climb. So one of the only times we had to do a straight up rope climb. And so 2018, power up, hang from a small bar, and also lift robots up off the ground. Those are not common. 2019 was lift your own robot. 2020, a hang and a spin. This is the first time they've had us spin a field element on the field. And with all of these, I want you to think about like the history at first. You want to be inventive, creative as you're trying to design your own game, but you also kind of want to like have it be recognizable as a first game. All right, so here's the question. You should see up at the top of your screen an annotate button, and you should be able to use a stamp, like an arrow or a question mark, or probably a question mark's not the greatest thing, but I want you to show using the stamp. How many times do you think we were required to do a bar hang or hang, lift your robot? Just do the grab a bar and pull down. Okay. Good. Ooh, interesting. I also feel like some of you are going to argue, which I get because this is robotics and we argue about everything. And so I think there's going to be some people who are like, well, but technically, which is always, if you ever start a discussion with somebody where the first words is actually or technically, yeah. So I will say this though, these are all really, really good. I think you can make an argument that it was only 5. Some people might even be able to argue 7. But I would say based on my count, let me see, I got to get out of the state. There we go. Based on my count, there are 6 times we were asked to do a bar hang, specifically a bar hang. Let me do this. All right. So what I want you, like, and for that, these are specifically ones where you had to grab onto a physical bar and lift it. The other thing is that some people might get, so there were 2 times we were asked to climb, and you'll notice that I put ultimate ascent into both of these. That's because, so Steamworks, I would say, is an outlier because we had to climb a rope, and that wasn't a bar. The other thing, the reason why ultimate ascent is in 2 categories is because every one of the first 5 in this category of bar hang, it was just grab a bar and lift up. But ultimate ascent, it was more complicated. You had to grab a bar and then climb to the next one and climb to the next one. So that's why I come up with this and have ultimate ascent into 2. So if you don't include ultimate ascent as just a straight up bar hang, it's 5. If you consider Steamworks to be a climb, bar, so I get it. You can anywhere from 5 to 6 are all correct. Okay, so there's how. The balance bridge occurred twice, and a robot lift occurred 3 times. In 2 of those were lift other robots, and 1 of those was lift your own robot. And I say all this because I want you to think about these as you're trying to design your own game. So that's all the preamble. I want to get to what we're going to talk about is kickers, catapults, climbing, and winches, and how we do that. These are some situations we're going to be going into. Then we're going to talk about motors and decisions. And I got a couple other spots that I'm going to stop and ask you guys to do the stamp question again. So kickers, it's all about a sudden release of power. You're going to want to use stored energy if you can. And what that means is either springs, bungees, pneumatics. You want to have a good latch mechanism to hold it because that's going to be kind of scary and dangerous. You want to have a secure lock for safety. And this is the huge problem. You want it to be extremely secure and lock, but you also want a fast, good release. And those are competing needs that you have for your design. This is first, and that's everything has those. This is a design from the Minnesota team. They called this Thor's hammer. They're out of Alexandria. It was a really simple, sweet, beautiful design of using stored energy. Because the hammer, they just had a motor with a mechanism. And once it got past here, there was just like a little bolt or a little post that held it. Once it got here, the thing would just smack. It was very, very brilliant, very simple, very easy to reset. Now, catapults. Make sure you have enough power and enough stopping power. This is the thing that people don't always think about. They calculate everything needed to send the game piece flying, and that's great, except make sure your frame can handle it. There was a Robot in 3 Days team that was building a catapult for aerial assist, and they bent the bejeebers out of their frame. You just got to be careful for that and test it a lot. The other problem with kickers and catapults is how do you reload them? These are very powerful. These are very massive amounts of stored energy. So you want a very nice, simple, easy way. This is a couple. We're going to get into these. These are cam gears, or this is called the choo-choo mechanism, and you can see right here. You just have a motor on a gear, and what happens is it's connected at this pin and here, and then this bolt, as it rotates, it pulls it down. And this one shows you it in motion. So once it gets to there, whing, the sucker just sends it flying. Now, this is glorious and wonderful. And yes, thank you. Please, if you love these designs, or if you've used these or you think they're great, somebody just put a stamp on there. That's nice. I like that. And this has a lot of benefits. The one major drawback that people will point out, and you have to be careful for, is you can only support this gear on one side, and that's problematic. There's a lot of forces going on, so that's something you have to be careful of. You have to contemplate and think about, and make sure you're planning in for that. Make sure you can handle that. This is another type of mechanism where they just have a cam gear, rotating, or snail gear, or bullion gear, depending upon what you want to call it. But essentially, it all works the same. This one, I kind of love this design. I'm a big fan of this. This is the robot from the Robo Wranglers, Team 148 out of Texas, and this was the design that they did for Breakaway. And you'll see that one a little bit later on when they did their climbing. So climbing, this one's a lot of fun. We've had to do this quite a bit. There's some scary options like this. There's some other terrifying ones, but there's two main methods: pneumatic pistons, and a winch. Now, we're going to try to start a fight here. Vote. What do you think is best for trying to lift your robot in a straight bar lift? Pneumatics or winch? Vote with the stamps. You can do hearts or check marks or arrows, or you can vote. Some people are typing into the chat. I got 2 votes for winch in the chat. Really? Okay, good. Wow, really? This will be good news for my team, my students. Yes, okay. David, correct. The question is how fast? Yes. The answer is, okay, whenever anybody first ever asks you this or this, it's always a trick question, because the answer is like, well, that depends. It depends on what you want. In this situation, like me personally, I'm not a huge fan of pneumatics. I know they're glorious and wonderful. My problem is we always have like 1 need, not 5. And if you're just putting pneumatics on for one thing, it can be problematic or difficult. But there are a lot of benefits to using pneumatic pistons for a climb. Mostly because climbs are required at the end of the game, a lot of the time, almost always. And you can have a ton of stored energy in those pistons. And because at the end of the game, there are teams where battery's running low. You've maxed that sucker out by driving around like a maniac, and there's nothing left to lift the bot, which takes a lot of juice. Now, so stored energy, that's very, very helpful. Here's the question though. I love the look on that kid's face. That is priceless. You can tell this is the first time they've tested this because he looks terrified. Also, look at those pistons. That's insane. That is an insane length. And some teams are like, you think that's big? We got like 40-foot ones. And I'm like, okay, great, that's amazing. But that's always the question you have to figure out here. So if the pistons can handle the distance, if you can afford them, we got a question. If there is, just jump in if you want to unmute and ask a question real quick, or type into the comments. But so pistons can be wonderful for that and do the job very well. The downside is, I mean, you're limited with the throw, you're limited with how far it'll go, and there's other aspects and issues with that. Winches. So when it comes to winches, it can be a lot more complicated. You need to have brakes. You need to talk about latches. We're going to talk about using them as springs and bungees with gears and sprockets and how those are different. Winches are really great if you need a high torque application. This is another picture of a team climbing in 2010 breakaway. The other thing that's nice about winches is you can keep it really small. Pistons, you basically have to be able to be half the height of your total height. So that can be limiting and problematic. Winches can be really nice for that. This one kind of scares me a little bit because what you're looking at is the drum is coiling up metal cable, and that's awesome, except metal cable can be problematic in that metal cable can tend to bind and catch when you're trying to spool it and unspool it. There's another team climbing in 2013 for the pyramid climb. That was a fun year. Now, here's the other. So hanging and climbing. This team, if you can climb on a scissor lift, you know, God bless you. That's amazing. That is a task. That's a very impressive. That's a big ask for a scissor lift, but there are teams that have done amazing with that. This is also pretty impressive here. Climbing while lifting another robot. That's some intense stuff. And this is where, like this year, Steamworks, you pretty much had to build a winch. There was no other way to climb up a rope than a winch, essentially. Now, when it comes to there's a lot of complexity, or there can be. You want to make sure that cable is secured. The last thing you want it to do is grab some wires and rip those out of your robot as they're moving around. You have to be careful. If depending upon what you're using, you need to leave room on the drum. Because if you're using a strap, which is what we prefer if we can, the diameter changes as the drum winds up the strap. So make sure there's guide cables. Make sure you always have tension. It's pretty easy to add a little tensioner on a spring of something somewhere. That's always a nice thing to have in there. The return, some people will use weights. Usually we're up against, 120, but you can use weights or springs. Springs are very easy. Like, don't make your motor do everything, like it's not the end of the world to throw some bungee or some surgical tubing on that sucker to give your motor a little extra help. But the other thing we're going to talk a lot about is you need to have some sort of brake or ratchet. The last thing you want to do is to have your motors try to hold the weight of your robot. This is a huge no-no. You're going to blow your motors out. Now, the other thing, you want to have cable in both directions. I know we're tempted to be like, well, we just need to pull it up, or in this case, pull down to lift the robot up, and gravity will do that. No, it won't. I know students are like, well, gravity's always there. It's reliable. And I'm like, yeah, but no, it's not. It will screw you over. And if you've been to my other presentations, you know that is it's Murphy's Law. Something can go wrong, it will. The other thing you need to know, so you should very, very calculate the torque, calculate the speed, figure out exactly what you need, how much you need. And our rule of thumb is double it. And I'll talk about that a little bit more when I talk about the motors. So gravity return is not recommended. Braking device, we'll talk about the braking device in just a little bit. So here, this is another option here. You need to have some sort of braking to make sure you don't have any backdrive, because in this situation, this is a catapult, and they've just done lots of bungee here, and you can see, it's sometimes hard to see, but there's a ratchet device. They took a ratchet, like just a tool, and threw it on the robot because they're using a 1/2-inch hex, so they just used a 1/2-inch wrench. Now, some people will say tools don't belong on the robots. I think Vex has something like that on their website. And on the one hand, I totally get it. On the other hand, it works. It works really well. Everybody has one. You can get them very affordably. I mean, I don't know, man. If you want to be fancy about it, I guess, lop off this part and bolt it down somehow. But if it works, it works. I don't really see the reason behind making teams feel bad for using a functional device. You have to be careful about this stuff. You don't want, there are some wrenches that are very, very simple, and they're not able to handle the force. So you want to test that and make sure. Our rule of thumb, I'm I need to lose some weight. I'm I'm about 2 robots is how I measure my weight. And so our rule of thumb on my team is it has to be able to hold my weight. So if I can be suspended from it, then it's fine. And that maybe, I don't know, maybe you don't have situations like that. So here's a couple more. If you want to get fancy, you can buy a ratchet sprocket, mount that, put some sort of device on there. This is a modified version that a team put onto their robot just from a ratchet strap, for like tie downs. And we've not used this, but I really kind of want to use this. Just the seatbelt from a car. And the main reason I'm intrigued or kind of want to do this, I always thought it'd be really sweet to have a seatbelt ratchet mechanism on the robot, just because the seatbelts are inertia. Like when the car's inertia, that's what actually clicks the ratchet in. So I feel like you could theoretically, without too much difficulty or modification, have it set up so that the trigger lever, the automatic locking mechanism, could be set up so that once your robot leaves the ground, then it engages, and then you climb up, and then when you go up, it could be really nice. I don't know. We haven't done it. We haven't seen it, but I am intrigued. This is another image from If It Works, Shut Up. This is technically a clutch. This is like a disc brake, like you see on a bicycle, because literally this team just ripped a bike brake off of a bicycle. And you know what? That works. If it works, yeah, I got no problem with that. But this may not be the most reliable thing. So yeah. The other thing is this: any gearbox that cannot be back driven. So some teams would be like, oh, it's fine. We'll use the window motors or the seat motors or something like that, because they're not back driven. And that's fine. That's awesome. Except the problem is, if a motor can't be back driven, that means that it's going to be extremely inefficient if you look up the numbers on that motor. And when you're talking about lifting your robot off the ground, you really want it to be as efficient as possible so that you can get your robot up off the ground. Otherwise, it's fairly problematic. Latches. This year, for last year, the 2020 Infinite Recharge, we built this gloriously complicated, lovely latching mechanism. And then when we tried it out, we realized we didn't need it. But this can be extremely helpful in certain games, especially if you ever have to do a lift off of a bar that is vertical. And I'll show you that in just a moment here. It's on the slide. So this can be extremely helpful. There's a lot of teams, they just do hooks, and I get it. That makes sense. Except you see a lot of times, sometimes those hooks fail, sometimes they fall off. A latch mechanism from below can be very, very effective, because you don't have to do that. You've probably seen teams trying to get onto the bar and they miss, or they go, it's problematic. There's latching mechanisms. This one that you see in the bottom of the screen, that's from a car door. And if it's strong enough to hold me as I, go up against the door when we're going around a corner, it's probably fine for the robot. And there are other similar mechanisms where teams will just have a Y, and it'll just go up to the bar, and then the latch clicks on like handcuffs. So they're fairly simple. Okay, it depends on how you build them. But there's a lot of ones that you can just get off the shelf. The thing is, and this happened to our team one time, they tend to be an afterthought, and that's not a good idea. They should be front and center. This is what I'm talking about. This team, Robo Wranglers out of Texas. This blew me away. Honestly, it's the most insane method. They're like, how about we just lift the robot on a pivot? And what you can't see in this short little clip here is that they put their numbers on the bottom of the robot, so that when they did this little flip maneuver, they would do it pointing at the other alliance. So the other alliance would see their numbers, which, near as I can tell, that's the closest a robot gets to mooning another team by throwing that up there. So basically, they're just kind of, and that's glorious, and I love them for it. All right, now, so those are the mechanisms that we use for interacting. So this is a question. So we're going to move on to power, motors, things like that, and how they relate, because that can be an issue with a lot of teams in a situation. So When you ask a group of first robotics students, you say, what does power mean? You usually get answers like faster, which makes sense, but is not true. And then they're like bigger, which not even close, kid. To which they're like more electricity, and then they're just like more, just isn't just more. And that's, yeah, this is the problem because this is a huge concept in first. So what does power really mean? I want you to vote with stamps which one of the 4 equations that I have up on screen is the answer for what does power mean. Do the annotate, you can do hearts, stars. I feel like stars would be best for this one, but good. I just started. Oh, okay. Gold star. Nice. Okay. Okay. There you go. Now, some of you are, yeah, good. Force times velocity, got 2 up on the screen. Yes. So it's a trick question again, because everything's always a trick question. But also this one's a trick question that's trying to be nice, because this is a trick question where every answer is correct. And this is also why kids get so logically confused about what power means, because so the official definition of power is energy over time. But what kind of energy? If you're talking about electrical energy, then it's current times voltage is what power is equal to. And that is perfectly correct, and that's accurate. That's electrical energy. Mechanical energy, it's work over time. So that's where you get this confusion, and some people might not even, so power equals work over time, work equals force times distance. So if you substitute force times distance in for work, you get power equals force times distance, time. And then if you include this, velocity is distance over time, you can substitute in velocity for distance over time. So power is equal to force times velocity, power is equal to current times voltage. But the thing you have to realize, like, you're only given, you only have so much current and so much voltage. You've got to make sure and do an electrical audit. And I'll show you some slides that have information on that. But the thing I want you to understand is you have got to choose between force and speed. You cannot have both. Your motor has a power rating, the watts. Watts are joules per second. It's energy over time. And if you don't run through and do the calculations, you're going to be in trouble. And there are a lot of times where teams will want, like, so they'll have an elevator that's used for their game piece. And so they want it to go really fast. And that's perfect. That's great. That's sweet. That makes sense. Except then they're like, and we'll also use this to grab onto the bar and climb. That requires a massive amount of force. And you must choose. You're either going to have a game piece manipulator that's slower than you want, or a lifting arm bar that's not as powerful, it's not as forceful as you want. It doesn't give you as much force. And so this can be problematic. And there are some teams that they just say, we blow out motors, and that's fine. Okay, if your solution is to buy more motors, that's probably not the best solution. You can do it with one motor, but you need to have gearboxes or something like that. Speaking of motors, what a lot of teams don't necessarily, so a lot of teams are pretty good about doing calculations and finding the right motor, but then we don't often necessarily take into consideration all the gear reductions that we're doing. Our rule of thumb on my team, and what's recommended by most teams, is figure out how much force you need and double it. Something else that I've seen teams do, and my students do all the time, they calculate the force needed for the motor, but they forget the fact that this is going to be connected to a gear. Well, force changes as distance changes. So that's, work, force times distance. So the farther away you get from the point of rotation, the weaker the force is. You have to make sure that you calculate that in. Also, stall current. You got to look at those. Stall current can, blow out. It'll trip your breaker. Inefficiencies due to binding. So spur gears. It's kind of like the classic 90%. Chain sprocket, worm gear, planetary gears. When you think about this, if you're doing a gear reduction, a couple of either sprockets or gears inside your gearbox, you can lose up to 35% of your power. That is huge, especially if you were just barely making it. You don't want to overtax your motors. Also, how do you know? Well, this is a motor curve. If you've never seen a motor curve, you need to, somebody on your team should know how to do this. Somebody on your team should be in charge of a spreadsheet with these curves for your team. And you want to look for optimal things here. You can see on your screen that like we have speed and RPMs is over here. And then over here you have current, efficiency, and power in watts. And they're all labeled and they're all different things. And you got to be careful. You got to make sure that you're not screwing things over is basically what's going on here. Okay, so you got to look for the most efficient situations. Usually you see these ones right here, the green one for efficiency. And so you have to like make sure that you're working at the peak efficiency. We usually go for efficiency and then try to figure out a motor that will give us the speed and the power necessary at that level. Okay, good. I was wondering, where are the labels on this thing? So green is efficiency. Red is current. I mean, you don't want to be drawing too much current, and you want to be at max power. Make sure you're calculating this, because a lot of students, they just grab the motor and they look at the thing, and this motor is rated and has this much power and this much speed. It's like, yes, that's true, but at what situations? This is a chart where this talks about if you have 4 sims and you're driving 50% of the weight. This is a classic chart. If you've not seen, somebody on your team should have seen this. It's talking about how fast you're pulling the robot. Basically, it's doing calculations for you with current draws. And then you'll see down here, we have situations where bad, basically red's bad. You can probably figure that out. But it's just make sure you know the limitations of your robot before you start driving it up against the wall. Now, question. So how do you decide? Well, if you've been watching and listening along, there's a theme. The answer is it depends, and there are options. So it's a lot more than just thinking about, it's a lot more than just what's the best manipulator. So my team, what we do when we start designing for manipulators, I make them go through this slideshow because I have it accessible, but I'm like, and I make them go look and research and find out, are there other years that have had similar situations going on? Is that like, look for those. And you start with all the manipulators that exist. And you got to do a lot of research to get that number going. Then you have to look at what are the manipulators that work specifically for this game, be it the game piece and or the field manipulation that this PowerPoint slide's more focused on. And this is very important, your strategy. And that's what a lot of teams don't necessarily like. This is where it gets dicey and problematic, because my team, whenever we analyze the game, I know, so like kids always want to jump straight to designing and building, and we could build this thing to do this thing. And I'm like, okay, wait, pause. What's the strategy? What's the purpose? What's the point? If you're trying to build a robot that can drive crazy fast, or a manipulator that can go really, really fast, then if you want to do this other thing, you might need a separate manipulator for that. And this is just such a difficult balance. You want your manipulator to do as many things as possible, but at the same time, it can't be all things to all aspects. A lot of times, First does that on purpose. They'll have like 2 game pieces at a time to make us focus and choose, and then like a third activity that we have to do. The other thing is this: consider your tools, skills, materials, manpower, budget, time. Like, you may not be able to build the most amazing manipulator with like a double 4-bar linkage. If you don't know what that is, maybe you can build it, maybe you can't. A scissor lift. My team, like, scissor lifts can do glorious, wonderful, magical things if they're properly built. They have to be built with great care and great craftsmanship. And my team is not there in the metal shop, so that's a situation where it's not necessarily the best fit for us. So decisions. Summary for decisions. Look around, see what works and what doesn't. Know your design objectives. Know your game strategy. stay within your capabilities. And some general advice. I know everybody says this, but they say it a lot because teams don't necessarily follow it. Understand the dimensions using CAD, make sure you know that. Make sure you got somebody on a spreadsheet with the motors doing all those calculations for you. Keep it simple and make it well. Some of you have probably heard this already, but poor craftsmanship can ruin the best design. We had one year, it was the ramps, power up year. We had a mentor from another team come over and look at our ramps. And he asked one of our kids a bunch of questions. He's like, I love this design. It's beautiful. And their robot was very similar. They had a very similar design. They had almost the exact same ramps, but they had a different mechanism for lifting it. And I pointed out to this mentor who was being very kind. I'm like, yes, but ours don't work. He's like, oh, you built it horribly, but it's a brilliant idea. And the kid and I were like, thank you? Like, yeah, I'm gonna go with thank you. And we had a great design that we had poorly executed. And that's the nature of the beast. You need to have all things together. Refine the design. We all are in that situation where we tested and it works great and we're so happy and it's so exciting, except what we don't realize is it's going to fail on the 10th one because we're asking too much of our motors. And so make sure that you figure out what's going on, make sure that you're able to check everything, get spare parts, figure out stuff. There's an old joke about like a mentor he was stress testing the robot and he was kind of, throwing all of his weight on it. And the kid's like, what are you doing? Stop it. You're going to break it. He's like, better to break it now than have it break during competition. And we know that thought process, but the kid's like, hey, how about we just don't break it? Like get off the robot. And so you got to balance that between stress tests. But the other thing I want to advise you with, this is supposed to be fun. Throw some googlies on it. This is our robot, Jarvis. We put googly eyes on because we put googly eyes on almost every year that we can. And we put a mouth on it this year, which is a new addition that I'm particularly fond of. But I love that. Also, we treat Jarvis like a family pet. And so name the manipulators. Name it with, make up funny names, make up inventive names. So things like that. Those are just some things. Finally, some credits and recognition. This PowerPoint was a lot more of my own, but my other PowerPoints, and a lot of the information in here with the winches and stuff, I took a lot of that from PowerPoint I found from Bruce Whitfield. He's a mentor of Team 2471. As I was doing research, it appears, I wanted to ask Andy this question when he was on beforehand, but I didn't want to like interrupt with this stuff. But it appears that Bruce took a lot of that from a PowerPoint that Andy made. But as I was digging through, it was like archives. It was like unearthing layers of FIRST Robotics presentations. And eventually I came back. Greg Needle is apparently the origin for several of the slide bullet points in this presentation. And then finally some resources here at the end. Behind the Design has a ton of really good resources. Team 254, Cheesy Poofs, they build amazing robots and they put a lot of their information out there for teams to check out and see their designs and see how they did it and how they built it. Team 358 has a lot of resources available if they have like a FIRST Robotics electrical Bible. So if you got a new kid on the team and he wants to be on the electrical team, but your senior graduated last year without transferring knowledge, then that's where you go. We have links on our website for new recruits and give information. And 358 has some beautiful resources available for those rookies that need help, just to get them the general basics that are hard to spend time with. Now, questions. This is my contact information. This presentation, along with this video, will be posted on the Jumpstart website. And if you have a question, you can type it into the chat or just unmute your mic. And I'll be happy to answer anything. If it's about a specific slide, I'll happily go back to whichever one.
Hi, Mark. This is Andy Baker.
Hey, how's it going?
Good, good. Thank you for the credit. That's very nice. Within First, there's a lot of people that use a lot of other people's presentations. Like with my presentation during the last session, I definitely give Nick Lawrence a lot of credit because he made a lot of that presentation, and I just stole from him. And I mean, he works here at AnyWork, so
Oh yeah.
not that he had a choice, but anyway. But yeah, you're right. I think a lot of things in my manipulator presentation that I've developed over the years, a lot of those things did come from a presentation that Greg Needell did.
Yeah. Okay, good.
But also, I think with regard to presentations, if you can give credit, great. But if you can't give credit, you can't know where everything comes from. That's fine too. The betterment of the community by having these presentations is much more important than making sure all your credits are right. So if you never give me credit any time, I'm fine with that. That's fine.
Okay, good. Well, there's one in Manipulators Part 2. I throw you under the bus a little bit when it comes to scissor lifts, because on one of your slides you had, I do not recommend this. And it was like Andy Baker. So I'm like, yep. That's not me, that's him. So
that would be a good presentation in itself, debating those issues, because I've learned over the years that so many different teams still debate drivetrain issues or lift issues, all kinds of stuff. And there's not one way to do this. That's one of the cool things about it. So my opinion is one, and your opinion might be another. That's great.
Well, and actually, the funny thing is, one of the people that I stole from Whitfield, Bruce Whitfield from Team 2471. He has a slide where he's like, "Never use this for a launching mechanism." And a few years later, his team did exactly that. So I think anytime we as coaches or mentors say, this is not a good idea, our kids will prove us wrong. And sometimes intentionally work very hard at proving us wrong. But that's, never say it's a bad idea. Because I've seen teams go to championships with scissor lifts that my team could never build.
Sure. Yeah, it kind of depends on, well, yeah. I'll let some other people talk, but that's a good debate.
Yeah, definitely.
Hey, Mark, can you put up the website slide a little longer?
Sure. There we go.
Thank you.
Sorry about that.
Any other questions?
I see somebody was kind enough to put the Team 358 into the chat. I can do that with these other ones as well. They're pretty cool. Any other questions?
I don't see anything coming up in chat right now.
Okay.
Yeah, there's a wealth of information. Thank you.
Yeah, it's always I always want to make sure I save time for questions at the end.
Mm-hmm.
It's always hard to, it's always a balance. I don't ever want people to drink from the fire hose, but at the same time, that is what's going to happen.
Yeah.
So
it's very good.
Thanks.
All right.
Well, as I said, I stole a lot of it, so I can't. So.
Well, I liked your energy too.
Oh, thank you.
It's very engaging. I
will say this: all those slides at the beginning with the images from the fields for all the years, that's brand new. I just did that yesterday, so. I've been wanting to do that for a couple of years, finding all those fun ones.
Yeah, it was good to have those images, and then the video too. Very nice.
Also, I didn't realize that endgame was not always a thing. Because my first few years in First, they were like 2010, 11, and 12. They all these glorious, wonderful end games. And in 2014, I was so sad that we didn't have. I was just so confused.
I picked up on that, your emphasis of that. There was no end game.
Yeah. Well, yeah, I was just crestfallen, and like halfway through the season, my kids are like, "Give it up, Durand. They're not going to come out with an update end game." And I'm like, "Well, maybe they could." And they're like, "You're delusional." So yeah.
All right. Well, very good.
If anybody has any other questions, though.
Okay. Yep. And so otherwise, we will reconvene in about 6-7 minutes just to get set up going. But the next one program is Programming and Driving Robots over the Internet. So I'll give everyone who wants a little bit of a break to do what you need to do, and then we'll get back here in a few minutes. Thank you.